In this video, we're just going to continue with more of the L'Hopital's rule problems. So we've already looked at the basic indeterminate form, which is 0 over 0 and infinity over infinity. It is these two forms that allow you then to use L'Hopital's rule. But they are not the only indeterminate forms. There are other indeterminate forms that will allow us to manipulate our function to get it into the 0 or 0 or infinity over infinity. I'm not going to go through every example. I want to go through about 2 or 3 more with you. So the next form I'm going to look at comes from a function that would look like this. Suppose I want the limit as x goes to infinity of x squared times sine of 1 over 4x squared. Now, just like with before, you can go ahead and plug in your infinity and you're going to get something crazy. You're going to get infinity when you plug in infinity for x squared. And then when you plug in infinity for 1 over 4x squared, remember, you're not plugging in infinity. As x goes to infinity, x squared, of course, goes to infinity. As x goes to infinity, 4 times x squared goes to infinity, and 1 over a number that's getting larger and larger and larger approaches 0. So the 1 over 4x squared approaches 0, and sine of 0 is 0. So this is what we say the form of infinity times 0. If you ever have infinity times 0 with 2, and you're trying to take the limit of 2 functions that come out to this, we can turn that into either 0 over 0, infinity over infinity, by just using a reciprocal rule. So for example, we all know that if you had 2 variables, a times b, wouldn't that be the same as a divided by 1 over b, or better yet, a divided by 1 over b. Or it could be b divided by 1 over a. A times b is the exact same function as a over 1 over b and b over 1 over a. It's a reciprocal rule because if you divide by the reciprocal, you're multiplying by the function itself. So we can utilize this rule to turn one of these functions over the other. Now think about it. In doing that, think about this for a minute. The limit as x goes to infinity of x, of course, is infinity. If I take the reciprocal of x, doesn't that go to 0? Okay. Same as if you're going to 0. The limit as x goes to 0 of x is 0. If I take the reciprocal, one over as x approaches 0, when you divide 1 by a number, sorry, I accidentally wrote infinity there, it needs to be 0. As x approaches 0, this actually goes to infinity. So this idea is if you have a product, one's going to infinity, one's going to 0, and you reverse and multiply by the reciprocal of one of them, you will then get either 0 over 0 or infinity over infinity, and then you can apply L'Hopital's rule. Now, obviously, I would suggest going with the easiest function of the two. So we have x squared or sine of 1 over 4x squared. There's our 2 functions. I'm going to take the x squared term. I mean, you can certainly do it with the 1 over 4 over x squared, but that's going to get a little bit more complicated. I'm going to keep the sine in the numerator, and I'm going to flip this to 1 over x squared. Well, if we try to plug in infinity, we're now going to get 0 over 0. All right, so that allows us to go ahead and use L'Hopital's rule where we take the derivative of each. So now you want to just remove this for a second. you want to take the derivative off to the side. We need to figure out what the derivative of sine over 1 over 4x squared is. And that's simply going to be the cosine times, don't forget chain rule, d dx of 1 over 4x squared. And you can apply, I mean, some students actually like to use the quotient rule on that. You don't have to use the quotient rule. You can just do 1/4 times 1 over x squared, 1/4 of x to the negative 2. And take that derivative, and you will actually get negative 1 over 2x cubed. So d dx of 1 over 4x squared is that. So when I plug it in, I get cosine of 1 over 4x squared times negative 1 over 2x cubed. And now I need the derivative of 1 over x cubed, which is x to the negative 2. So it's negative 2 sorry, pen stopped for a second, x to the negative 3. So it actually is negative 2 over x to the negative 3. I'm just going to rewrite these a little bit differently because it looks really complicated, but it's not that complicated if you think about it. You have x to infinity, and keep my cosine of, 1 over 4x squared. And I'm just going to write this as negative 1/2 times 1 over x cubed. Okay, I just broke it up. And then I'm going to write this one as negative 2 times 1 over x cubed. Yeah, I don't know why I wrote that negative 3 there. I apologize. Okay. Only because you can clearly see these cancel away and the negatives cancel away. Okay, that's the only reason I did that. Also, let's limit x goes to infinity of 1/2 divided by 2 is 1/4, so that's 1/4 then cosine of 1 over 4x squared. And when you go ahead and plug in infinity, you're basically taking cosine of 0, because 1 over 4x squared is going to go to 0 as x goes to infinity. So it's 1/4 times cosine of 0, which is 1/4 times 1. Cosine of 0 is 1. And our answer is 1/4. So there are other forms where you can manipulate, but keep in mind you cannot actually apply L'Hopital's until it is in 0 over 0 or infinity over infinity form. I'm not going to do an example, but even if you had a limit where you had infinity minus infinity, usually you can combine fractions and then apply one of the other rules. So there's different things you can do. But I do want to spend a couple minutes going over another type of indeterminate form, and this comes from a funky little function that looks like, what's the limit of x going to 0 of x to the x? Which leads us with a 0 to the 0 power. And this can come up in different forms as well. You could have something like a 1 to the infinity power, or you could have infinity to the 0 power. These are all indeterminate forms. They're all indeterminate forms. And you might, students, get confused. Well, how can 1 to infinity be indeterminate? Because remember, and if you look at the function I actually gave you, we're not actually taking, it's not 1 itself. It's a value that's approaching 1 as another value approaches infinity. So in 0 to 0, you also might be thinking, well, anything to the 0 power equals 1. Not necessarily. It might come out to 1, but you cannot just assume it will, because what you're actually taking is a value as it approaches 0, not the 0 exponent itself. So you got to be really careful with these, and these are considered indeterminate forms, and you got to do a little work to evaluate them. So let's take a look at this one. And anytime, if you recall, back in your pre-calc classes, you dealt with a exponent that had a variable in it, you usually would utilize the properties of logs to solve it. So why would we do that? Well, let's take a look. So how do I utilize the property of logs? Well, I got to introduce it as an equation first. So I'm going to let y equal my limit as x goes to 0 of x to the x power. Okay? Because the second I can introduce it as part of an equation, I can then do all sorts of things to it, as long as I do them to both sides of the equation. And one of those things I can do is take the natural log of both sides. So I can say, okay, I want ln of y, and then I want ln of the limit of x goes to 0 of x to the x. And hopefully you're thinking, oh, that makes sense, because you can do stuff when you take the natural log of things. But before we get there, one of the things is, I don't want you to forget, when you finish the problem, you need to come back to this part. Okay, we got to come back to that, and I'll explain that when we get there. All right. Fortunately, there's this great property that says the natural log of the limit is the same as the limit of the natural log. So in other words, the natural log of the limit of f of x is the limit of the natural log of f of x. Those two are the same thing. So that means we can manipulate this by pulling the limit on the outside and have ln of x to the x. Now we can apply a log property, and hopefully you'll see where that will end up helping us. So I have ln y now equals the limit of x ln x, because we know that ln of x to anything equals, you can pull that exponent out front. It's just a standard property of natural logs. So keep in mind, where does L'Hopital come in all this? Well, L'Hopital can't come in until we have 0 over 0, infinity over infinity. We're not there yet. What we do have, though, if you think about it, when you take the natural log, this goes to 0. What is the natural log of x as x approaches 0? The best thing there is, try to remember your natural log graph. You can only approach it from the right, so technically when I wrote this equation, I forgot to put the plus. You're only looking at it from the right. So when you do get a problem and you say, why are they only going from the right? Well, it's because, especially like this, if it's a natural log, there is no graph coming from the left. So technically, we would put that little plus sign on all the zeros, and I just forgot that. Not on that one. So when you approach, you actually go to negative infinity. And negative infinity, positive infinity doesn't matter. You still have a 0 times infinity. And we said, oh, wait a minute. With 0 times infinity, we can manipulate that using our reciprocal rule. Again, I'm going to suggest going with the easiest one. Sorry, thicker marker. So I have ln y equals the limit as x goes to infinity of ln x, and I'm going to just turn that into a reciprocal, because you can see clearly now that I'm going to get infinity over infinity, or infinity over remember it's coming from the right over positive infinity. It doesn't matter, positive or negative. But we're good. We got infinity over infinity. We can now apply L'Hopital. So this equals, according to L'Hopital's rule, the limit as x goes to 0, we all know what the natural log of x is. That's just 1 over x. I mean, natural log, sorry. Derivative of natural log of x is 1 over x. And the derivative of 1 over x, which is in our denominator, that's x to the negative 1. So it's negative x to the negative 2, or negative 1 over x squared. You can simplify that if you need to. Take it out of the fraction and write it, go back to your basic math, right? Is 1 over x times x squared over 1. So the whole thing just comes out to negative x. So now we have, natural log of y equals the limit as x goes to 0 of negative x. When you plug in 0, you get 0. So now I know the natural log of y equals 0. How do you solve for y? You've got two options here. You can just get rid of the rule for natural log and say, that just means e to the 0 equals y, or take the e, raise each. You can do each side, remember? Take it e to that, and you get y equals 1. Okay? Either way, you're going to get y equals 1. Okay? So the answer itself is not 0. Y equals 1, which means if you look back in the beginning, y equaled the limit. So the limit of x as x approaches 0 of x to the x does indeed equal 1. Now again, just because it is to the 0 power doesn't mean you can put it equals 1. It just so happens it does in this case. Okay. I do want to do one more of these. So this next one, I guess it's a little bit more complicated, not too much, but this is a pretty important one. And I'll say it again as you move into Calc 2. All right. So let's do one more of this type. Okay. And this one is going to be the limit as x approaches infinity of 1 plus 1 over x to the x. Okay, so if you were to plug in infinity, the 1 over x would go to 0. You would get 1 to infinity, which again, you want to say, but that probably equals 1. But you got to remember, x itself is not necessarily, it's as x approaches infinity, not equaling infinity. You can't really equal infinity. So we have an indeterminate form, but we cannot apply L'Hopital's rule yet. Because you have an exponent that is a variable, we're going to go with the y equals. Natural log of both sides. I'm going to take the natural log, but I'm going to move it into the inside. So I'm going to get the limit as x goes to infinity. I'm just going to skip a step here. When you take the natural log, I can move the x out front, so it becomes x ln of 1 plus 1 over x. All right, which is going to give me infinity times 0, because the natural log of 1 is 0. And because I have infinity times 0, right, because this is going to give me that would be infinity times natural log, and ln of 1 is 0. Because we have natural log of infinity times 0, I'm going to apply the reciprocal rule. So ln of y as x approaches infinity. Of course, I'm going to do the 1 over x, much easier than trying to take the reciprocal the other piece. Now I have 0 over and 0. Now I can apply L'Hopital's. What that lets me do is actually, I write LH to say I am now going to apply L'Hopital's rule. Okay, we'll do the denominator first. We already know that that equals negative 1 over x squared. If you recall, when you take the derivative of a natural log, it ends up being 1 over that function times the derivative of the function. Well, the derivative of 1 plus 1 over x, the derivative of 1 is just 0, so that goes away. You need the derivative of 1 over x, but the derivative of 1 over x we know is negative 1 over x squared. So those end up canceling rather nicely. Oops, I didn't mean to write. Natural log of y is going to equal the limit as x goes to infinity of just 1 over 1 plus 1 over x. When you plug in x as it goes to infinity, the 1 over x piece is going to go to 0. So that whole thing is just going to equal 1. So the natural log of y equals 1. This time I'll just use the rule for natural log. Remember doing this? It just means e to the first equals y. And if e equals y, then the limit as x goes to infinity of 1 plus actually equals e. This ends up being kind of a cool definition for e. Something that you will, again, utilize in the second half of Calc 2. You might recall from your first lab, when we first did limits, I asked you to find for me the limit. It was x approaches 0. I believe it was some of 1 plus x to the 1 over x. I had you do it numerically on the lab where you just plugged in a bunch of numbers, I believe, and what you found out is it came out to approximately 2 point blah, blah, blah. And I had asked you on that lab, hey, do you know what this number reminds you of? And it was e. And it's just a different version. So what I want you to notice that in going to 0, or the difference between going to infinity and going to 0 is the reciprocals. See, 1 over x became x and x became 1 over x. They are both useful definitions of e that you will get back to in Calc 2. Okay, so there's a couple more L'Hopital problems for you.